So that puts me at number 4 next. Now there is a typo here. That should be 5 meters cubed, not 5m3. So that needs to be moved up there, and we will start our question. So I'm going to read it for the first time, and I'm going to circle things that I think are important. An open topped. Okay, that's going to be important. Open top. That means no top. Rectangular wooden box is to be built with a square base. That's going to be important. It's going to have a capacity of 5 meters cubed. That's a volume measurement. Material for the sides are going to cost 1.6 per meter squared, while material for the bottom is going to cost more. It's going to cost $2 per meter squared. Okay. Find the dimensions that will minimize cost. So, cost is to be minimized. When I write that, a whole bunch of things come flooding into my head. If I'm going to minimize something, I need to find its first derivative. If I'm going to find its first derivative, I need an equation for it in terms of one variable. So the very first thing I do is I try to get an equation for it. Before I do that, let's get a picture. So it's a square base, so I'm going to draw pretty close to a square. I'm not going to worry about measuring. And then I'm going to overlap. Now what I'm doing here is I'm trying to trick my eyes into seeing a three-dimensional object on a two-dimensional piece of paper. And then I look away for a minute and I look back and I try to see it in this orientation. Here's my base. My base is going to have x and x because they told me it was a square base. And I'm going to have a height. I'm not going to make it x because they didn't tell me it was a cube. So h can be anything at all. It might turn out to be a cube, but right now I don't know that. They also told me that there's no top on this puppy. So there's no top. I need to remember that when I start working with this. Now, be careful. Not all of these rectangular boxes that we do are going to be square-based. I think the two I did in examples were square-based, but they don't have to be. If they are square-based, it means something. It means that the 4 sides are all going to have the same area. But it doesn't have to be that way. Look at the Kleenex box like we said in class. I could have X, I could have W, and I could have H. This side and this side could be the same, but this side and this side would be the same, but different to the ones on the other two sides. Keep that in mind. Okay, so I need to minimize the cost. So I need a cost equation. So if all of the material costs the same, then minimizing the cost would be the same as minimizing the amount of material I use. Now think about that again. If all of the material costs the same, then if I use the smallest amount of material, that'll be the lowest cost to build it. But that's not the case here. The bottom costs more than the sides. So there's a little bit of manipulating that we can do here to get the lowest cost. So what we need is a cost equation. So a cost equation is going to be $1.60 per meter squared for each side. So per meter squared of each side. And it's going to be $2 per meter squared of the bottom, or the base. Should have used base because it's less letters. That's my cost equation, but I can do better than that. The area of each side is going to be given, well, hold on here. This is 1.6 meters squared of each side, but how many sides are there? There's 4 of these puppies. So I need to show that. So there's 4 of them. And the area of each side is x times h. Plus $2 for every square meter of the bottom. There's only one bottom. So I don't only have one of these. And it's going to be x squared, because that's the area of the bottom. So 1.6 times 4. I think that's 3.2. 4 times 1.6. Oh, I was really wrong. 1.6 times 4, it's actually 6.4. And this is going to be plus 2x squared. Now this is pretty good. We're doing all right. But I can't take the derivative of this because it has two variables. Two variables makes us sad. We want to be happy. We need this in terms of one variable. So I need to go back to the equation and find out how I can relate. I need to relate x and h. I need an equation that's going to relate those two. So, looking back up for something I haven't used, I notice this, the volume. Well, the volume of a square-based prism is going to be the area of the base times its height, which is going to be x squared times h. And they told us that this particular wooden box had to have a volume of 5 meters cubed. So here's my equation. I can isolate for x or h, it doesn't matter, but looking over here, it's going to be nicer just to plug in for h once rather than having to plug in for x's. So h equals 5 over x squared. And we put a little bubble around that so I can find it later when I need it. So I'm going to take h equals 5 over x squared. I'm going to do a substitution in here. So I'm going to get my cost. Now it's in terms of x only. 6.4 x 5 over x squared plus 2x squared. Now 5 times 6.4 is 32. So this is going to be 32x to the negative 1 plus 2x squared. And this is my cost equation in terms of x. So that's pretty cool. Put a box around that so I can give you marks for it. But remember, we're after a minimum here. We want a minimum. Minimize this c of x. So you want to minimize that c of x. So we're going to take its derivative, and it's going to be negative 32, x to the minus 2, plus 4x. Now that's my derivative-friendly form, which is great. And here's my solving-friendly form. It looks like this. So I'm going to get a common denominator of x squared. And that is my solving-friendly form. And if I want to rewrite that so it looks a little bit nicer, it'd be 4x cubed minus 32 over x squared. Okay, so what I want to do next is I want to take that and I want to set it equal to 0. Because that's how we get our critical values. Well, I've got an x on the bottom here. That's a little scary, but I know that I have a restriction. X cannot be equal to 0 because it is a dimension. And if x was 0, then I wouldn't have a box. Well, that brings me back to talking about the interval here. I haven't done an interval yet for my variable, but we certainly know that x must be greater than 0. Now, to get the high end of the interval, we think about h. We know that h must be greater than 0. Is there any value of x that's going to make h negative? Well, the answer is no. It's x squared. There's no way I can get a negative from 5 over x squared. Is there any way that h is going to be 0? Well, no. No matter what value of x I put in, I'm never going to get 5 divided by x squared being a number. So the truth of the matter is, x can get as big as I want, as long as h can get as small as I want. Now again, it's not a very good practical answer, but it's a lovely mathematical answer. As x gets bigger and bigger and bigger, no problem, I just make h smaller. That's my interval. Now that's an open interval, so I can't solve it looking at endpoints. I'd have to use an interval chart, or I can use the second derivative test if there's only one critical number on that interval. So that brings us back to here. So I've taken care of the restriction. So that means that I'm only really interested in that. I'm going to common factor out of 4. 32 divided by 4 is 8. That's going to be 4x minus 2. X squared plus 2x plus 4 equals 0. And at this point, we should all know that this is going to give me complex roots. So we can omit. And it's going to give me with only one root, x equals 2. So since I have only one root, I can use the second derivative test. To stay on the same page, I'm going to come way over here. Let's put a box around this. I'll come way up here and I'll say only one critical value on domain. So I have a choice. I can use the second derivative test or I can use an interval chart. It depends how ugly the derivative is going to be. Let's take a look at my derivative-friendly form. It's not too bad. I think we can handle it. So the second derivative is going to be 64 x to the minus 3 plus 4. So it's 64 over x cubed plus 4. Now we don't really care about the entire thing. We care about it at a particular point. We want to know if it's concave up or concave down right at x equals 2. So we put the 2 in. You'll get 64 over 8 plus 4. And to be honest with you, don't really care what the value is. Only care that it's greater than 0. That means that c of x is concave up at x equals 2. Which means if it's concave up, I have an absolute minimum cost when x equals 2 meters. And the height, I guess, at this point, if we go back, the height will be 5 over 2 squared. The height will be 5 over 4 meters. And those are my two answers. How we doing? We okay? I'm going to stop the video there, and I will be right back with the next one. Oh, wait, I don't think I finished the answers. Find the dimensions. I did. It also wants the minimum cost. So you're going to take this value of x equals 2. You're going to take this value of h being 5 over 2, and you're going to plug it into the cost equation. I'm looking for a piece of paper to be able to do this. I don't seem to find one. Here we go. So it's going to be, let's see, 6.4 times 2 times 5 over 4 plus 2 squared. So that 2, that's going to reduce. So 6.4 divided by 2 is going to be 3.2. So 3.2 times 5 is going to be 1.6 plus 4.8, so 9.6. It's going to cost you $9.60, I think, if I didn't make a simple error. If I did, throw it up in the comments and let me know. But I think we're looking at, here, let me do it all in one. 6.4 times 2 times 5 equals, divided by 4, equals 16. Oh, maybe I did make a mistake. Let's try that again. 6.4 times 2 equals times 5 equals divided by 4 equals, ooh, something's weird. 6.4 times 2 equals times 5 equals divided by 4 equals 16, not 1.6. And this is definitely going to be 4 plus 8. So I think we're looking at $24 if I'm not mistaken. But the way things have been going, I better put that in. It is. So $24 to make this box, not 9.6. All right, guys, I'm going to stop the video there, and we'll be right back.